dear participants, let us continue. Our next speaker is Mircea Petrache with the talk titled Uniform Measures in Euclidean Space. So,
thank you. So may I share my screen?
yes.
Okay. Let's see if this is the program. Okay. Is it visible?
Yes, it's visible.
Okay, so thank you very much. I will try to be, I was predicting to be a bit shorter, so I will try to be short to keep in track with the schedule. And so this is, thank you for very much for the opportunity for being able to share this research and these open questions that that appear in this research here. So this is joint work with Paul Laurent, which is at University Paris 7, and I am here in Chile, in Santiago de Chile. Also, the question that I'm going to talk about is to see what could be uniform measures. So a uniform measure or uniformly distributed measure is a measure for which if you take, you are in a space, in a metric space, and you have a random measure over this space, and you can have sometimes the property that whenever you take points in the support of your measure and you fix a radius, then the measure of a ball with center pairs of points in the support with a fixed radius is always the same. So you can say that the measure doesn't see, when restricted to balls, doesn't see the difference between points in its own support. Okay, and so a special case of this, very natural to think about, is the case of homogeneous measures. So if I have the orbit of a subgroup of the isometries of my space, and then I define an invariant measure over this orbit, if the isometry group acts transitively on this set, yeah, which is true, then the measure will be homogeneous, yeah. So in this case, homogeneous, and in particular uniform, yeah. So homogeneous measures are a subset of uniform ones, and they are the most symmetric uniform measures, yeah. Also, one asks the question, will there be an equality instead of just the inequality, yeah? Is there an equality here? And then, in fact, to me, it was pretty surprising that there are at all uniform measures which are not homogeneous. So they are symmetric when one looks at balls in a way, but not in the symmetry is not really a geometric one over the whole measure. So these are the basic questions, and we are going to restrict, as the title of the talk was suggesting, we restrict to Euclidean space, right? So a very special metric space, which is already a lot to think of, have already a lot of open questions. This is not nobody is restricting anybody to think about only one space, and in fact there is a theory that was set up for arbitrary abstract metric spaces, and however this theory is even less advanced than in the Euclidean space for the general cases, right? I have to mention that for the sub-Riemannian geometry case, so this is the Heisenberg group, sub-Riemannian spaces, there are some results which are pretty close to the, they're following closely the theory in the Euclidean space in terms of how advanced they are. However, they are still, there is still more work to be done even in that case. But I think there are a lot. There are simple steps to go forward in the study of uniform measures for specific spaces. Okay, so the motivation of this theory in Euclidean space, especially, is coming from can be coming from the geometric measure theory. So in geometric measure theory, one wants to see for measures if they have rectifiability properties. Okay, so one predecessor of rectifiability of measures is simply to ask if you can say something more about the structure of a measure, knowing that, for example, the measure of balls, very small balls, is having a limit, has a power-like limit, right? So you can think what happens about a measure, if positive measure, such that there exists a power that, so that at all points, the measure of the ball of radius r divided by r to this power exists. What if this limit exists almost everywhere on the support with respect to the measure? So almost everywhere in the support. Well, then still this reserves a little bit of surprise. First of all, that alpha, the power, needs to be, if this limit exists almost everywhere, the alpha is constrained to be an integer. So the measure will have a dimension, which is an integer dimension. And furthermore, you get that the measure is rectifiable, is basically absolutely continuous with respect to Hausdorff measure of that dimension, supported on an alpha, the same dimension rectifiable set. Okay, so this theory is the one of the cornerstones nowadays, one could say, of geometric measure theory, which is had a history through the whole past century. It started with work of Bezikovic, which was especially focused on the case of alpha equal 1, dimension equal 2, then later generalized by Moore for general D. And the proof that alpha will be an integer in general was given by Marstrand. And finally came this result of Price, a 100-page long paper, very influential for the geometric measure theory community, in which he was proving this result together with other that I will not enter into. And there are the Mattila book of geometric measure theory, and there are the Lellis notes on rectifiability of measures, where one can learn this, and it's organized in a nice way for studying it. And actually, where do uniform measures come? They come already. You can imagine here that if the measure is really close in a way to be a power law, then maybe it can be well approximated by measures that are uniform and where the balls all have volume equal to a power, or up to a constant times a power of the radius. And in fact, this happens. And actually, if you see the precise version, that is not the most quoted one of the Price theorem, in fact, you can see some interesting phenomenon that he discovered also in the same paper, which is that the lim sup of this, if you only know that the lim sup is bounded away from the lim inf, I mean that you don't really need to have a limit, but you need only not too big oscillations, then you still get the same result. And in fact, this is due to a classification of an initial type of classification of what are the limits, the possible limits. You cannot have any limit. You just need to exclude things that are far away to be a plane in order to get this rectifiability. Well, a rectifiability for a set, it means that the tangent space, that it has generalized or weak tangent spaces. And it means that you can approximate this measure by a measure on a plane, the area measure on a plane of dimension alpha. And so basically in that classification of the first classification of Price was saying that away from measures that are given by a plane is not any small perturbation of a plane that can be a limit of this kind, which will be a uniform measure. If you take the limit of this rescaled version of the measure, it will give you a uniform measure. And then he was proving that the planes, the measure restricted to a plane is a uniform measure, and close to it, there aren't uniform measures up to a distance given by 1 plus c. So in other words, there is a geometric quantization, if you want to think of that way, of measures close to the class given by planes. Okay, so and that part of the paper of Price was to introduce uniform measures on Euclidean space, and he was ending up with this open problem. So it's funny to read this open problem, because it says it is not difficult. So UD is the uniform measures on RD. Is it not difficult to give a simple description of uniform measures in 1 dimensions, right? Or in 2 dimensions with bounded support. Yeah, and then he says, see this paper, which we are going to look at later, which is Kirchheim-Price. Another paper by Kirchheim and Price. But then he says this funny sentence: to give a similar description of uniformly distributed measures in higher dimensions, higher dimensional spaces, is a natural, though probably hopeless question. So this is it's pretty depressing for somebody who wanted to study this. But yeah, of course, the whole classification is pretty hard. I think this is still open. However, we are trying to do some first steps, some steps forward in this. Okay, so just to let me mention, if you think of U1, the uniform measures on the real line on R, then this is pretty it's a more elementary problem. And then basically you have multiples of the Lebesgue measure, or Hausdorff one-dimensional measure. Yeah, up to multiples you have this, or you have the counting measure on the integers, or you have the counting measure on z plus any real number. Sorry, any real number union z, for example. Yeah. So of course, then you can do translations of these discrete measures, but you have these choices, right? So uniform measures either are the Lebesgue measure, or you have a periodic one, or you have two periodic, two copies like that. And in particular, these are all homogeneous. All of these have the property that there is a subgroup of the isometries acting transitively on the support of the measure that is keeping the measure invariant. Okay, so they are all homogeneous. And these ones, you can also find that, oops, I'm sorry for that. You can also find that they are all homogeneous. Yeah, so U2 with bounded support, so measures on R2 with bounded support, one can find that they are all measures which will be living on a circle, and on a circle they are just either the uniform length measure on a circle or a multiple of it, or you have a regular polygon. The vertices of a regular polygon, or you have the vertices of two regular polygons of the same number of vertices, which again are homogeneous measures, all the homogeneous measures. And already in R2, for possible uniform measures that are not of bounded support, then this is not known, the classifications, although there are no known examples that are not homogeneous, which means either the Lebesgue measure on 2 dimensions, or supported on a union of parallel lines, or parallel lines of 2 grids of equidistant parallel lines. In a way, the product of this measure on R times a line, or you can have lattices, and several copies of the same lattice which are all measures that come from actions of isometry subgroups. Okay, but these are known to be uniform measures, but the whole set of uniform measures in 2 dimensions is not classified completely. Other known results about classification, these are pretty close to being all the known results. But there are a little bit more. So basically, if you want to study this, there are these papers, the ones by Kirchheim and Price and Kowalski and Price, which actually were both around the year of 1987. And this one came late because, as it's written in this paper, it was already ready in 87, and then for some reasons of the separation of Czechoslovakia, where these people were working, it was hard to publish it for a long time. And then, so basically the results are that if you know that a measure, besides being uniform, is also dilation invariant, then there is even more restrictive, and you have only the case that this measure is a multiple of so the measure of a ball is a power of the radius times the constant. So these are something present in the paper by Price. And then this is the surprise here for me. It was a surprise that a measure which is uniform, a particular case of a measure which is uniform is this set C3, which is the set of points with real coordinates x, y, z, w, such that x squared is equal to y squared plus z squared plus w squared. So I call it the light cone. You can call it the light cone if you, but actually it's in a Riemannian setting. There isn't any Minkowski metric, right? So it's a subset, a submanifold of 3 dimensions inside R4, right? And and how does this come up? It's interesting to think about this a little bit, which is basically in R3. So this cone C3 here is actually, if you slice it, you can find slices equal to the sphere S2 in R3. So the sphere S2 in R3 has this property, that is that if you take a point on the sphere, not only the sphere in R2 is the orbit of the rotation group, so then it gives you a uniform measure, but also if you take a ball with the center on the sphere and you intersect, this is a little ball BR X, with X a point on a sphere, and it's a ball in R3, you intersect it with the sphere, the area of the intersection, BR intersected with S2, this area is equal to pi r squared, right? So you cannot distinguish S2 from being a subset of the plane in terms of how much is the area of a ball centered on S2, except if you take the radius enough large that this is larger, that this ball is very large and contains the whole S2 in its interior, in which case you will see the difference that this is stuck at the whole volume of the sphere, while the corresponding ball in R3 is going to be of larger and larger area. Okay, but for testing with small balls, S2 is indistinguishable from the plane. And using this property, you can convince yourself that by doing a decomposition of this C3, you can convince yourself that little balls with center on C3, as this point X is moving to infinity, it becomes flatter and flatter, but still it keeps having the same volume, 3-dimensional area of the intersection. This is basically based on this kind of miracle of that balls centered on the sphere S2 have the same area. In fact, you can now change the radius of this sphere, change R, and then it will still have always the same volume, the same intersection area as for a different R of these spheres S2. Okay, I hope some of this, I hope maybe I wasn't clear completely, but I hope some of this is become clear and that you could do possibly the computation on your own with this information. And Kowalski and Price go a little bit further and say that if I am restricting to measures in any space of a measure on RD in RD, which has this growth where the balls center on the support of the measure have a area power, and the power is d-1, like the volume of the sphere of the ball of dimension d-1. Well, in that case, they have a classification in this special set of uniform measures, which is saying that, well, either you have this light cone times r to the d-4, which gives you a codimension 1 surface in RD, or you have a hyper or you have a hyperplane. Yeah, this supposing that mu is also having connected support, right? Otherwise, you can have copies of hyperplanes, or several grid of hyperplanes. Okay, and so basically there is a classification for codimension 1 uniform measures. And the only surprise comes from this light cone. But this only for those uniform measures for which you fix how is the volume of balls. Yeah. So and then the other result, probably the best result we have so far is or like the nicest looking result is this result by Kirchheim and Price, which is saying that the uniform measure up to scaling is the measure of an analytic variety. Okay. So then there are other results which are saying that if I have again a measure which is going where the balls, which is a uniform measure, and the balls have a volume or like measure equal to a power, then the support must be regular, except on a set of dimension at most this power -3. So it's you know, there are many analytic varieties. Many of them have singularities, and then this result is saying that at least if you know that the measure is given by a power, then these singularities cannot be you have at least bound on the dimension of the singular set. So they must be a little bit lower dimension than the measure itself, than the variety itself, and much lower, k-3. And this is basically showing that this cone C3 is giving has a singularity. So the C3 has a singularity which just as the tip at the cone, the tip of this cone, which is exactly of dimension 0 inside the cone of dimension 3. So it's k-3 is sharp. The bound k-3 is sharp. And further, Dali and Imer also has worked in his thesis. This is his thesis work that he did with Tatiana Toro in Washington. He found other examples of singular cones, not only C3 but others, which are all based on unions of spheres S2, which are tangent to each other inside a space of high enough dimension. So here you have one sphere in R3, and then you take the cone of that and you get the subset of R4, but you could have many S2s in let me think, in RD minus 1, have many S2s that are tangent to each other and give you a cone in RD. And this, it will always be a cone of dimension 3, but higher codimension, which he proves that it is also a uniform measure. Okay, so many results work with power type. So uniform measure with where the balls have a volume equal to a power. But we were thinking together with this colleague of Paul Laurent, we are thinking about uniform measures, more general, the general ones, right? And then you introduce the distribution function, which is basically this function that gives you the volume of a ball of radius r centered at a point in the support of the measure. So this is the distribution function. And what happens for general distributions functions? Okay, so for general distribution function, this is the first result, the Kirchheim-Price structure result. So the Kirchheim, first of all, the result, it's short enough that I can give a proof. So basically, the first thing is to show that the measure cannot grow too much. This is based on the fact that you could cover, by a covering argument, you can show that the measure of a ball of radius large r is bounded by a power d, which is here you have d, which is the dimension of our ambient space, times the distribution function, right? So the distribution function really bounds the possible value of all radii. So f of r helps you to bound the radius, the measure for all r larger than this little r by a covering argument. And then this covering argument allows to make rigorous the expression of the integral of Gaussians with respect to uniform measures, right? So you can change variable in this integral. This integral converges due to the first fact, the bound here. And then you change variable and you find a function that basically there is a function which gives you the integral of Gaussians centered on the support of my measure, only in terms of the distribution function of the measure. And now you can check that. So if I have my measure and then I have a Gaussian, I cannot draw a Gaussian centered on the support, and then I have another Gaussian that is centered away from the support. Well, then the ones centered on the support will have the largest integral with respect to mu, because the Gaussian decays with the distance. And so if I take this function fxs, where I have Gaussians of variance s, variance parameterized by s, and I have one point in the support and I have another point wherever I want it in space, then this actually doesn't depend on the choice of x0. And then you have that this value in general is smaller than this other value, except when x is also in the support, in which case the f is 0. So you have that x is in the, also you can finally deduce that x is in the support of the measure if and only if for all s this fxs is equal to 0. Now fxs is due to the growth condition here, this is an analytic function. And so you have that the measure is in the intersection of analytic varieties, the zeros of analytic functions. So it is an analytic variety. So you can use all this theory of analytic varieties in order to understand a little bit better your measure. And then the last part, which says that it will be a constant times the area, the Hausdorff measure of the correct dimension on this variety. This is again given by a little trick using Bezikovich differentiation and looking what can be the germ of the volume. You know, you see the volume of a ball, you think of the germ of this function, take r going to 0, and then this must be in, again, due to the measure being uniform, doesn't depend on the point in the support that you have, and that easily gives you the the fact that actually the measure must be a multiple of the volume measure, at least away from the singular set. Yeah, and then in the singular set, well, that actually you can the singular set will have a measure 0. Yeah, and so you can say almost everywhere it is a multiple of the volume measure. Okay, and then so this was the first part, and then the second part that one can do for general F is a differential geometry algorithm. Now you know by this previous result, you know that you have an analytic variety, and now study this variety. And so we can apply at regular points, we can apply Taylor series and study what can be the Taylor series of the volume. So you parameterize your submanifold, take the volume of a ball, intersect it with this submanifold, take the Taylor series, and now this Taylor series, you have a lot of coefficients depending, you can express it in terms of the curvatures, of different kinds of curvatures of different orders of your manifold, which correspond to geometric information. So you chase around this geometric information inside the Taylor series, and possibly study the case R going to infinity. Yeah, so you have a local near to 0 and near to infinity, the things can become simpler. And this is the strategy of Kowalski and Price. They did these steps, including the one with the control at infinity, using Taylor polynomials of degree up to 4. And in our case, we were looking only at one-dimensional measures, but with Taylor polynomials of any degree. So it will be enough to look at degree up to 2D. That this already includes all the curvatures of my lines, my one-dimensional measures. And so the results that we have are that if I have a uniform measure, yeah, here I forgot to say that mu is a uniform measure. If you have a uniform measure, which is the Hausdorff measure on a curve, so this analytic variety given by the result of Kirchheim and Price is one-dimensional. It's equivalent to say to be uniformly a uniform measure, or it will be a toric knot or a generalized helix. Yeah, so there is a classification, and basically these are the curves whose all of which curvatures are constant. You know, all the ones that are given in the Frenet-Serret paradigm for studying curves. And then in particular, all uniform measures of that kind are homogeneous, right? There is no surprise there. And then you can go a little bit further and think about uniformly distributed measures, which are one-dimensional. What are the connected components? The connected components form a discrete set and are all congruent to each other. And if they are helices, we can say a little bit more that axes of these helices are parallel. So there are many helices which are translation of each other, but we cannot say more about the whole distribution of these helices, all because the discrete measures that are uniform measures are in general not classified. Yeah? So this open question, for example, for uniform measures, the whole classification of uniform measures in R2, this is open, and discrete measures that are uniform measures and that they cover the whole space, they are not classified. We think they are just lattices, but we don't know. And so just lattices or translation or several copies of the same lattice, but we don't know. And then some details of the proof to give you a flavor where, because maybe one can try to extend this from one-dimensional measure to two-dimensional measures. So the proof is going like that. First, you write the Taylor series for a curve, and you can fix. Well, maybe you can forget about this part. This is not so enlightening now. Some normalization, and then you want to look about the distance of a point in a curve from the origin in terms of these vector coefficients of the Taylor series. And then you have this other Taylor expansion starting with t squared. And then you look at f of r, and which is the distribution function, or it is the measure of points in the curve that have a distance to the origin smaller than r square, smaller than r, or the square to the distance smaller than r square. And then the Taylor expansion of this fr needs to be independent. It is the same as long as I choose the origin along the curve. And then the Taylor coefficients here, they have a interpretation in terms of these and in terms of the coefficients here. And so one finds that this inductively can be proved that if the first two h plus 1 of these coefficients are constant, then the first curvatures of my curve are constant. So the curvature, the torsion, and the higher dimensional torsions. And then these derivatives of these being 0, then I can go to the next value of h, and this formula simplify using the Frenet-Serret theory. And then so in the end, one can find using this the result. Okay, so here I finish with my talk. Thank you for listening.
Thank you for your fine talk.